So this is rarely used, and the symmetric monopolar is much more used. It means the absolute voltage of both at the same time. Another one is both voltage and current are controlled by changing the firing angle of converter. The only one we can control in the LCC HVDC system is the firing angle alpha, or the extinction angle in the inverter side gamma. This is the only one we can control. And all the other systems, all the other voltage, current are decided by the system parameters. The control process can be described as the equation in this page. The VDOR times cosine alpha is the DC voltage at the rectifier side, while VDOI times cosine gamma is the DC voltage at the inverter side. The RCR is the equivalent resistance of the rectifier side, and RCI is the equivalent resistance of the inverter side. RL is the resistance of the DC line. This equation is very easy to help us understand how we control the system. We can control the alpha, the gamma, and also the VDOR or VDOI can be slightly controlled by changing the transformer type changers. According to the different control targets, the control mode of HVDC are listed in this page. The constant DC voltage control and the extinction angle control is usually adopted in the inverter side to maintain the DC voltage. Constant DC voltage or current control is adopted in the rectifier side to maintain the DC current, as we can remember to current at the rectifier side and the voltage at the inverter side. So cyclic benchmark HVDC model is a monopolar HVDC system with a 12-pulse bridge converter. This is the simplest HVDC system, and its rated voltage is 500 kilowatts, rated power at 1 gigawatts. There are fixed capacitor filter and dampers filters in AC side. This is the equivalent AC system model. The rated voltage level is 345 kilowatts in the cyclic benchmark model. The calculated magnitude of the equivalent impedance is 47.4 ohm. According to the definition of short circuit ratio, the short circuit ratio is 2.5. Although the equivalent impedance of inverter side is different from this one, its SCR is still 2.5. You may try to calculate it and you will find the same answer. This is the basic model of converter transformer and the converter. The two converter transformers are in YD and YY connection respectively. The ARD in the picture is the measured firing angle. It is here, the measured firing angle. And the GRD is the measured extinction angle. The AOR is the firing angle order. The AOR. This is the only one we can control in the HVDC system. So this is the most important signal in the system. And the KBR is the blocking signal of the converter. It is used to block the system in emergency situations. The rectifier gets the firing angle order AOR from DC current control. The PI regulator is the basic DC current control mode. This is how we get the triggering signal AOR. The CMR here, maybe I can put it here. The CMR here is the current measured at rectifier, current measured at rectifier. The CMRS is the per unit value of CMR. This signal is also a delayed signal to prevent the disturbance of the signal. The CORD here the CORD here is short for current order. It is coming from the VD core. VD core, which is the voltage dependent current order limit. We'll introduce it later. The C error is the differential between CMRS and CORD. The beta is the trigger lead angle, and the sum of firing angle alpha and beta is equal to pi. So it plus by pi, we can get AOR. It is clear that if there is a difference between the measured DC current and the DC current order, then PI regulator will change the firing angle order until the measured DC current is almost the same with the current order. However, the range of the beta is limited to 0.52 and 3.054 in radio, which is 30 degrees to 175 degrees. So the alpha is limited between 5 degrees to 150 degrees. 5 degrees is the minimal requirement of firing angle order. If firing angle reaches this value, the rectifier will lose its control of the DC current. The controller of inverter side consists of 3 parts. The first part is the VD core control in the blue rectangle. And the second one is the constant current control. And the last one is the constant extinction angle control. I will introduce them one by one. The input signal VD core is the VDCI here, the VDCI, which is the DC voltage measured at the inverter side. The gain factor of here, G is 2 to 1000 because the basic voltage is 500. And the MPVS here, it's the capacited DC voltage of the meter line in perennial per unit. According to the explanation of VD core, there are 2 yielding points in the VD core curve. The one is 0.4, 0.555, and 0.91. When there is a decrease of DC voltage owing to the AC fault, and the DC voltage is lower than 0.9 pu, then VD core will decline the current order according to the measured voltage. But if the DC current is lower than 0.4 per unit, the current order will not continue decreasing in order to prevent the overvoltage during recovery time. The minimal of the VD core, VDCL, and current order CO from system dispatcher will become the real current order for DC system. This is the current order from the dispatcher CO. The input of constant current control at inverter side is CMI. The current control input CMI, which is the signal of current measured at the inverter side. The output of it is beta, this one, the output, which is the leading triggering angle in the inverter side. The delay regulator after CMI is also used to form the per unit CMIS. This one, this is the similar with the one in sending terminal. CMIS is divided into 3 parts. One is used to calculate the compensated voltage. This one, it is multiplied by 0.01 and get the compensated DC voltage MPVS. This is because the voltage in the receiving end should consider the flowing current. If the current is high, then the voltage at the receiving end will be lower. The other one is used to times with MPVS to calculate the power value in per unit. The last one is used to compare with the current order, C order, CORD, which is C order.
The differential between them is the signal of the C area. For inverter side, there is a current margin control. This control is used to coordinate the current control between rectifier and inverter. Usually, rectifier converter places the lower of current controller. It will not lose its priority for current control until its firing angle comes to 5 degrees. In order to maintain the stability of the DC system, inverter converter has to take charge of the current control in this scenario. Except for this, current margin control will assure the priority of rectifier's current control. The last part of inverter control is the constant extinction control, which is the control in the most of the time, control applicable most of the time. The input of the control is the gamma measured at the inverter side, which is the minimum value of the GMD and GMS, as you can see here. GMD and GMS, the minimum value. These two signals are the minimal extinction angle of two converters, the YY converter and the YD converter at the inverter side. The gamma mean, the G mean or gamma mean, is the constant extinction order 0.2618 here, as you can see here, 2618. This is 15 degrees. The G area is the differential between gamma mean and the gamma major. Notice that there is a sub-branch from C area. That means when DC system is in fault state, the extinction angle order will be added with DGEI, which is used to prevent commutation failure. Beta G is the leading trigger angle generated for constant extinction control. The bigger one between beta G and beta C will be the final leading trigger angle. The firing angle order at the inverter side, AOI, is equal to pi minus beta. This is the whole control of the inverter side. This is the overview of HVDC control at the rectifier side. The DC voltage UDC is sent to master control and VD core. The master control or mouse C calculates the current order and sends it to VD core. VD core changes the current order according to the value of UDC. Whether to put the margin control is based on the state of converter. After that, the current order is sent to the current control amplifier to form firing angle order. Now I want to introduce the HVDC in CSG to you and show you the development process of HVDC technology. First, the CSG covers 5 provinces, namely Guangdong, Guangxi, Yunnan, Guizhou, and Hainan. Serves 240 million people within around 1 million kilometers. We have rich hydroelectric power in Yunnan, and which is the western part of the China, while the main load center is in Guangdong, the eastern part of China. The length from Yunnan to Guangdong is about 2,000 kilometers. So we need HVDC technology to transmit the hydroelectric power from Yunnan to Guangdong. Up to now, there are 11 HVDC projects in CSG, and the transmission capacity is over 37 gigawatts. Over 1/3 of the power consumed in Guangdong are coming from Yunnan province. since we have just lose our connection, so maybe we can take a break for 5 minutes. We come back at 3:05. Okay. I don't know where are we. Where do we get lost from which slide? This one or the previous one? Previous. 他在哪说？Max time 是吗？我没看到。怎么？没看到啊？
Because we lost handling and this slide. 应该就这样了 ，on this slide。你要不把它缩小，不4-5个 slides 的那个。
那我要重新共享。是不是？我把它作为共享又共好。
This was the slide。是不是这个？之前对啊。
Please tell me from which slide do we get lost?
应该5到目前，这是我看到的，往下。我刚刚在回忆令，我给你跳出来。
Maybe we can start from the CSG grid overview. We'll start about 4 minutes later.
Configure of CSG network 就是。
Hello? I can't hear you clearly.
Next slide.
This one?
So shall we continue now?
Okay.
Okay, I will continue to introduce now. Up to now, there are over 11 HVDC projects in CSG, and the transmission capacity is 35 gigawatts. Over 1/3 of the power consumed in Guangdong is coming from the Yunnan, using the HVDC and HVAC long distance transmission. The 500 kilowatts Tianguang HVDC is the first HVDC in CSG. The transmission line is 960 kilometers. The rated power is 1.8 gigawatts. The system was put in service in 2021. Before this project, the hydrogen power in CSG transmitted by 500 kilowatts AC system. The transmission distance are limited. This project is built by Siemens, and the picture is the side picture of the sending terminal. It's over 20 years ago. 6 years later, in 2007, the Guizhou Guangdong 2 HVDC project is put into service, which with rated power increased from 1.8 to 3 gigawatt, and the transmission distance increased to 1225 kilometers. CSG, which is us, are responsible for system study, system design, equipment specification, control and protection simulation test, and also commissioning test. Here now we have 16 years of HVDC system experience and has completed 11 HVDC contracts. And there are still 3 ongoing contracts, including 2 overseas projects, which are MVP project in Philippines and a Kilo project in Chile. With the power demand continually greatly increased with the economic development, only 3 years later, we found that the 3 gigawatt is still too small. So we built the 800 kilowatt Yunguang ultra high voltage DC project, which is the first UHVDC project, with the voltage rising from 5 to 800 kilowatts, and the power increased from 3 to 5 gigawatts. And this system was put into operation in 2010. This is the footprint of Yunguang UHVDC project. You can see there are 4 warp holes as the other picture, but are placed in different model. In 2020, we built Lu Gaozhao HVDC project. This is the first project to upgrade an existing 2-terminal system into a 3-terminal system. We are doing so because the electric power in Guizhou here is no more abundant. So we don't want to waste the capacity of the HVDC system. So we extended the HVDC system and built a 3rd terminal. This one, 3rd terminal to Yunnan. So there are more energy waited to be transmitted in Guangdong. Our HVDC technology has also promoted to overseas market. This is the overview of MVP in Philippines, for example. MVP is the 2nd HVDC in Philippines for regional AC grid interconnection. And the system is under commissioning now. Now we can come to the VSC HVDC technology and also its application in CSG. VSC HVDC is short for voltage source converter based HVDC, and it appeared later than LCC HVDC. The VSC HVDC was first used in wind power integration. VSC HVDC is more suitable for offshore wind farm over LCC because, first of all, the VSC can reverse the power transmission line without change the polarity of the DC voltage. So it provides black start the capacity for offshore application. This is the
main reason why VSC is used in this scenario. Because the wind farms have no other AC source, they need the HVDC to provide black start ability. The LCC cannot be used to black start the network. Secondly, the VSC do not rely on strong AC grid and can provide reactive power support to wind farms, while LCC need to consume reactive power from the grid. Last but not least, there is lower filtering requirement for VSC. We have just seen the huge size of the AC filter in the LCC, but by cancelling the filters, the VSC has much lighter weight, saving the platform footprint. The cost over footprint is much more sensitive than in onshore applications. With the development of the VSC projects, now they are also used for high power transmission with overhead lines. We can come back to that later. This slide shows the basic working principle of VSC. The AC side voltage of VSC HVDC is fully under control, and the output current is controlled by controlling the voltage drop between VCE and between VCE and VLE. Both the active and reactive power are controllable in VSC projects. For active power, if UCE lacks ULE, the converter is working on rectifier mode, otherwise invert mode. For reactive power, if UCE is bigger than ULE, the HVDC is working on capacitive mode, otherwise inductive mode. You can see that both the active power and the reactive power are controlled and they are decoupled. You can control active power and reactive power as you wish. This is a VSC converter with two-level converter. As can be seen from the figure, the output connected to the positive power or the negative power at any time. The output of UCE can be connected to positive power or negative power. So there are two levels. This is why it is called a two-level converter. As for the voltage of each IGBT is limited to several kilowatts. So we need hundreds of IGBT connected in series to form the high voltage. In LCC, there are a lot of thyristors connected in series. And here we have a lot of IGBT connected in series. The difference is the switching frequency. The switching frequency of LCC is 50 Hz. The voltage and current are controlled by the field angle alpha. And the switching frequency of VSC is much higher. The drawback of this topology is that we need high voltage capacitors. We need connected lots of IGBT in series, which is very, very difficult because IGBT is much harder to keep the voltage even. And the switching frequency should be high enough to control the harmonics generated by the converter, which makes higher loss. So in order to improve the power quality, three-level converter can be used. For example, the MPC topology is the most used three-level converter. As can be seen from the figure, the output can be connected to the positive power, the negative power, or the middle part. The middle part is formed by the two capacitors. The middle part, it can be connected to the middle part. So we get three levels. So there are three levels. We can reduce the number of IGBT connected in series by 50% and also get better power quality with same frequency. The main limitation of two-level and three-level converters includes it it is really difficult to control dynamic voltage sharing of serials connected IGBTs and diodes in nanoseconds. We need to strictly control the parasitic parameters of the driving system and the main branches. Secondly, the IGBT should operate at high switching frequency to reduce the harmonics, typically 1 kHz to 2 kHz. So the loss is much larger than LCC, typically 2 to 3%. 2% loss means more than $208 million money wasted for each 1 gigawatt system. Sadly, the frequency is not high enough, so we still need harmonic filters, although fewer than LCC. In addition, we will have severe DVDT or DIDT use issue because the switching process of IGBT is much faster than thyristors. So the DVDT and the DIDT is more severe, and consequently, it will cause EMI issues. Due to these limitations, the capacity of VSC is much smaller than LCC for a long time. Then, Professor Marcotte proposed the MMC topology. It uses a lot of submodules connected in serials, avoiding serials connection of IGBT. This is a huge capacitor in every submodule. So the submodule don't need to turn on or off at the same time. Then we can get multi-level characteristic. For each submodule, the switching frequency is limited to 200 Hz, but the equivalent switching frequency at the AC terminal can be tens of kilos hertz. The harmonic is greatly decreased. No filter is required. The switching frequency is decreased. The power loss is also greatly decreased. So the MMC topology dominates the VSC technology nowadays. All ongoing VSC projects are based on MMC topology. This page shows the working characteristics of 2-level, 3-level, and multi-level converter. You can see the output voltage of MMC topology is quite similar with sine wave. We can get it from 2 level to 10 level to 50 level. When using 50 level, the voltage is almost a perfect sine wave, so we don't need any AC filters. For submodules with half-bridge voltage topology, there are 3 different working states. The half-bridge means we are using 2 IGBT connected in serials, and then the IGBT is connected in parallel with a capacitor. And considering the direction, there are 3 different working states. And considering the direction of the current flow through the submodule, there are 6 working modes in total. The block state, which is this one and this one, means both the IGBT are switched off. If current is in positive polarity, the DC capacitor is connected in the DC branch. When the current is in negative polarity, the DC capacitor is not connected in the DC branch. The deblocked switching means the deblocked switching in means the upper IGBT1 is switched on and the lower IGBT2 is switched off. The DC capacitor is always connected in the DC branch, so this is why it calls the switch in. If the current is in positive polarity, the diode D1 is connected, otherwise the IGBT1 is connected. The deblock switch out means the lower IGBT is switched on and the DC capacitor is always disconnected from the DC branch. At any time, the number of switched in submodules in every phase is constant, so we have a constant DC voltage, but the number in upper arm and the lower arm keeps changing, so the voltage at VAC keeps changing. We get a fluctuating VAC. By doing so, we get the sine wave and VAC. These are typical waves in the MMC. This one is the arm current. It includes DC bias, fundamental frequency, and circulating current. The harmonic can be suppressed by circulating current control. The valve side voltage and current are sine wave. So we don't need AC filter. This is the valve side voltage and the valve side current. We don't use no AC filter, and the waves are sine waves. This one is the arm voltage. It is also sine wave, and it is decided by the number switched in submodules. In the right part, this is the DC voltage. It remains constant because the number of switched in submodules between DC poles keeps constant. And the other one is the submodule DC voltage. You can see there is a big fluctuation. This is why we need the capacitance should be big enough to suppress the fluctuation. This is the main drawback of MMC topology. We need to use a lot of capacitors inside the topology. Although all the capacitors are low voltage, 2 kilowatts in. This is why it makes the system expensive. VSC has been developed very fast in the past 10 years. Voltage and capacity of VSC are now enough for further application up to 5 gigawatts. The 800 kilowatts and 5 gigawatts VSC has been put into service in 2020 by CSG. So it now has the same capacity, almost the same capacity as LCC technology. Similar to LCC, the VSC can be divided into different parts. And we will introduce the different equipment compared to LCC. The biggest difference is the converter valve. The valve in VSC is consisted of a lot of submodules. Typically, the basic element of VSC HVDC is submodule. And you can see this one, this is a submodule. As a submodule, you can regard it as a one thyristor as in LCC. This one will be much bigger than thyristors. So this is the typical submodule in MMC. It is mainly composed of 2 IGBT, the IGBT1, IGBT2, and a capacitor here, and 2 diodes. And also the bypass switch, here, the bypass switch. The bypass switch, I think it is a clever design because, you know, we connected a lot of submodules in serials. If one or several of the submodules failed, the bypass switch can be turned on, so there won't be a breakpoint in the branch. The equalizing resistor, this one resistor, is used to keep the voltage even. To trigger the IGBT, we need to trigger system, the control board in MMC. And we put this second element, all these secondary elements in this submodule, all these in one submodule, and they are energized by the capacitor voltage. So we avoid the energize of the power module from low level, which will be quite expensive. The transformer is also different from LCC. In VSC system, no harmonic will flow through the interface transformer, and it's mainly used to match the voltage level. In some scenario, we can even cancel the transformer if the voltage of DC and AC matches. In monopole system, the transformer is exactly the same as an AC transformer, so it will be much cheaper than transformer in LCC. We need to use a start resistor in the AC side. Otherwise, the charge of the capacitor, the huge capacitor in the MMC topology will result in large current. So it is usually used air insulated and air cooling type. And this is the side picture. And there is an arm inductor in each arm of the MMC to provide interface reactance and to suppress current circulation between different arms, and also to suppress fault current rising. This is a typical 3D design drawing of VSC HVDC station. The upper side of the picture, this one, is the AC side of the system, and the lower is the part is the DC system. Is the DC side. You can see most of the land of the station are occupied by the converter valve hole. There is no AC filters, so the AC yard is very small, but the AC valve hole is much bigger than those in LCC. There are 5 VSC HVDC projects operating in CSG. I would like to introduce them one by one in detail so we can know the development of the VSC HVDC technology. The first one is the Nan'ao project. Nan'ao project is the world's first multi-terminal VSC HVDC project. There are 2 sending terminals for multi-wind farms integrating in Nan'ao Island. The DC level is 160 kilowatts. The rated power is 200 megawatts. It's very small because this is the first VSC HVDC technology in CSG. And all equipment are installed indoor. They are put in a building. This is the first VSC HVDC and also a milestone of VSC HVDC project because it is put into service in 2013, 10 years ago. The DC line includes overhead line on the island, submarine cable, and also underground cable. These are pictures of MMC valves used in Nan'ao project. They are manufactured by Longxing, Nari, Xi'an separately. We are using valves from different manufacturers in the first project, and this helped China to build a strong manufacturer team. Up to now, there are 8 different manufacturer teams in China, which greatly promoted the technical iteration of VSC HVDC here. The symmetric monopolar configuration is adopted in the project because this is the simplest configuration in HVDC system. The system is grounded by a large resistor at the transformer's neutral part. As you can see here, it is grounded here. There is no DC offset at the AC side, so the transformer is an ordinary step-down transformer. There are more than 10 farms dispersed on Nan'ao Island connecting to the 2 110 kilowatts AC substations, and the multi-terminal system is a more economical option for integrating decentralized wind farms. We are choosing symmetric monopolar configuration because it requires fewer secondary devices, less space, less complexity, and can simplify transformer design. The capacity of the system is small. The reliability of the system, because it is a monopolar system, reliability is relatively low, but the reliability of the system is acceptable. When selecting the semiconductors, we considered the following aspects. First, the semiconductors should meet the requirement of rated current in normal operation and stand the peak value in transient situations. Second, with half-bridge topology, the DC side short-circuit current flows through the anti-parallel diode. So the diode should withstand the overcurrent until the parallel thyristors or the AC side circuit breakers have interrupted the current when selecting the DC capacitors in submodules, firstly, the total stored energy in all submodule capacitors of the converter should be big enough to suppress the voltage fluctuation. Then the final value is found by the result of a number of time domain simulations, mainly to investigate the maximum overvoltage during transient conditions. After installing the equipment on site, field testing is the final step to verify the system performance. This is the first time we do the field testing of VSC. We divided the field test into 3 steps, namely station test, two-terminal station test, and 3-terminal station test. In the station test, we test all the equipment inside each station and ends by running it at state-com mode. The 2-terminal and 3-terminal tests used to verify the overall system performance, including short-circuit test. This is the power step test result in 9R project. For the active power step response, the rising time is about 55 milliseconds, from 10% to 90% of the step hit. For the active power, for the reactive power, the rising time is about 80 milliseconds. They are quite fast. This is the power reverse test. The direction of the power flow between converter stations can be easily reversed according to the operation condition, and you can see here the power direction has been reversed within several seconds. The converter loss calculated based on the water cooling system. It is the inlet and outlet temperature difference. So we can calculate the loss. The converter loss in Jinyu and Sucheng station are 756 kilowatts and 629 kilowatts respectively, when 100 megawatts power flowing from Jinyu to Sucheng station. So the loss is about 0.6 to 0.5%. This is almost the same loss as LCC HVDC, while the valve of Qing'ao station is 448 kilowatts at full load condition. The startup procedure of the VSC HVDC as island mode with wind farm is usually as follows. First, converters of sending and receiving ends are charged through AC network. Then VSC HVDC system deblock and the AC voltage is set up at the sending end. Lastly, the wind farm are connected to system with current breakers. In this way, if the capacitor of the transformer in wind farm is close to the capacitor of the sending converter, the inrush current of the transformer may lead to an overcurrent in the sending end of converter. So that has caused a trip in Qing'ao station. Benefiting from the good control characteristic of VSC, the problem has been solved in the commissioning stage. First, the startup procedure is adjusted that the breaker of the wind farm transformer are closed before sending end converter deblocking. Secondly, the control strategy of the converter is improved that the step up is replaced by smooth driving of the AC voltage from 0.1 pu to 1 pu. So the inrush current of the transformer is avoided without additional hardware. The 9R project has achieved considerable reliability, which is comparable to LCC. Annual statistical data about system annual reliability is provided below. The availability can achieve more than 99%. The VSC system can change the direction and the value of power flow without flipping the polarity of DC voltage, which made the multi-terminal DC system a suitable way to meet the needs of both wind power delivery and the local power supply on island at the same time. A typical curve of the power transmission monthly is shown below. You can see the power can change significantly in short time, and the power flow has changed the polarity. The world's first multi-terminal VSC attracts interest from all over the world. By 2016, CSG has implemented 8 HVDC to deliver high power from western to eastern cities. So we are facing consecutive overload of AC transmission lines when HVDC blocks. You can see in this picture, if the DC system blocks, then the power load can change to the AC lines because the AC line cannot control the power flow. But the AC lines is not strong enough, so it will be overloaded and trip again. In this way, it may cause system stability problem and cause widespread power outages. So we built Lucy back-to-back VSC HVDC. It is used to deal with this problem, to enhance system stability and keep the capacity of power exchange between the Yunnan grid and the rest of the CSG grid. The 350 kilowatts, 1 gigawatt back-to-back VSC HVDC was put in service in 2016. Hybrid LCC and VSC technology is used in this project. Why? Because firstly, the receiving end of this HVDC is a weak system with normal effective short circuit ratio in severe conditions and sometimes even lower. This is critical for LCC HVDC, so VSC is required. And also, by 2016, the VSC HVDC is still quite expensive. To reduce the cost, 2 LCC is applied using different features of VSC and LCC. The combination of LCC and VSC in the same station achieve better performance. To reduce the investment and the power loss, the rated DC voltage of LCC units is selected at symmetric monopower and DC voltage at 160 kilowatts. Single phase 3 winding type of the transformer are used to save the footprint. The VSC unit is selected at symmetric monopower and the DC voltage is 350 kilowatts. This is much higher than LCC because the current capacity of the IGBT is much smaller than Cylestas. The rated reactive power is designed at 300 megawatt, while in STATECOM mode, the reactive power can be 400 megawatt. There are a lot of benefits by paralleling VSC with LCC. Firstly, it avoids the power loss while commutation failure when all the units are LCC. Secondly, due to the good fault write-through capacity of VSC, it reduces the power loss and active power impact on the AC system faults. Thirdly, the recovery performance of LCC units after commutation failure is improved and the voltage stability of the AC system is enhanced. And finally, the VSC unit is able to regulate the system voltage on the AC voltage control mode when the AC filter of LCC units are switched in or out, and helps to increase the capacity of every single active filter to save the number of sub-banks. This is the picture of Yunnan side converter 1. The 4.5 kilowatts and 1.5 kiloamp IEGT is used. At that time, this is the biggest IEGT we can find. The loss is about 0.55%. This is the Guangxi side converter. Wow. The 3.3 kilowatts, 1.5 kiloamps IGBT is used. The power loss is about 0.74%. It is higher than Yunnan side for 2 reasons. The first is that the IEGT used in the project has better performance. The other is that the loss in receiving end is usually bigger than the sending terminal. This is a comparison of Yunnan side and Guangxi side. except from the IGBT difference. The DC capacitors in Guangxi side is much bigger because the rated voltage of the capacitor is lower. A newly designed control structure is used in the project, help LCC and VSC to coordinate with each other and obtain best performance. This is the dynamic step test of VSC HVDC. The step response time is less than 60 milliseconds in the project. This is the fault right-through capacity test. The LCC and VSC are facing same AC voltage situation in test. You can see the VSC show great advantage over LCC. First, the DC power of VSC falls slightly, while the DC power of the LCC falls to 0. You can see here, it falls to 0. Secondly, the VSC HVDC provides reactive power support to the AC system. It provides reactive power support, while the LCC absorbed great reactive power from the system. This is the operation data of VSC HVDC. The VSC unit is often used to regulate the AC voltage of the power grid while keeping active power transfer because it has the capability of generating reactive power. Furthermore, just in the second year after completion, the usage of the VSC unit was up to 34 hours. This is a very high level. This is all for the VSC HVDC project. The Wudongde project is the 10th HVDC project in CST. It transfers 8 gigawatt hydrogen power from Yunnan to Guangxi and Guangdong, forming a 3-terminal system. This is the first 800 kilowatts VSC HVDC in the world. This is also the first hybrid LCC VSC project in the world. Before this project, there are already 9 LCC HVDCs located in load center in Guangdong province. If we keep building LCC projects, there is a risk that the AC system is no longer strong enough to help all the LCC system to restore from severe AC faults, as the LCC will absorb huge amount of reactive power from the AC system when restored from the AC fault. So by using VSC solution, we can avoid commutation failure and even provide extra reactive power support to improve multi-infield LCC, the other LCC HVDC, to restore from faults. So for 800 kilowatts of LCC, typically 2 400 kilowatts 12 pumps valves are connected in series. So to match the LCC, double 400 kilowatt converter are used in VSC. The biggest challenge of the system is the DC fault right-through. VSC has natural ability to deal with AC side faults. This is their advantage. However, because of the anti-parallel diodes of half-bridge, 2-level, 3-level, or half-bridge converters cannot deal with DC side faults. This fault current flows through the diodes and cannot be turned off by the semiconductors. So in this project, we use 4-bridge converters, which has a reverse blocking capability, preventing side short circuit, preventing DC side short circuit. The 4-bridge converter is more expensive than half-bridge converters and usually has higher power loss. To deal with this problem, hybrid VSC with a 4-bridge submodule and half-bridge submodule is proposed for this project for the first time. This photo shows the largest VSC station in the world, located in Guangdong, which is 800 kilowatts, 5 gigawatts VSC. The commissioning was finished and the system is in operation since December 27th, 2020, with a flawless performance. Here are 2 typical commissioning test results. This slide shows the test result of AC fault right-through. you can see the active power fluctuates slightly, just like Lucy back-to-back VSC. This is the instinct advantage of VSC. All of the VSC projects have this advantage. This slide shows the test result of a DC fault clearance. Here is the actual test photo when this fault was set. The DC fault was cleared by the VSC active control with reducing voltage. We reduced the voltage to 0 and then to negative values, so the DC fault current can be controlled to 0, and the system restarted smoothly, and the DC power restored with 85 milliseconds after the fault was cleared. The power loss is calculated using the inlet and outlet water temperature. The VSC converter loss is about 0.7%, and note that we are using 70% full bridge converters. Now, recently, we have further using back-to-back VSC technology in Guangdong province to improve power system stability. The capacity of the back-to-back system is 3 gigawatts per channel, and the 2 channels have put in service last year. In the future, we are considering upgrade LCC to VSC in receiving end to solve the problem of commutation failure of multi-in-field systems. We have already developed a technical solution for the upgrade, and this should take place in the next decade, as some LCC HVDC has been put into service for more than 20 years already in China. We are also using VSC HVDC to transmit offshore wind power. Offshore wind power resources are abundant in China, and many concentrate in the several provinces. Among them, Guangdong province has the largest offshore wind power resources. By 2025, the offshore capacity of the wind power transmission will be over 51 gigawatts. Now, we are working on a 2 gigawatt HVDC offshore wind project. The system is expected to put into service in 2025, and it will become the biggest offshore wind power project in the world. The system is a monopolar system because we can avoid using a submarine return press, which is very, very expensive in offshore wind power transmission applications. And also, we avoid using booster stations. The 66 kilowatts voltage was used in the overseas power system. That's all the introduction. Thanks. If you have any question, please don't hesitate to contact. Thank you. Do you have any question about my introduction?
Hello, my name is Rowan. I'm from Kazakhstan. My question is, do you plan to develop all LCC receiving ends to VSC, or only two stations?
Hello, I cannot hear you clearly. Can you be closer to your micro?
Okay. Can you hear me?
Yes, I can hear you now.
In the future, you plan to develop all LCC stations on receiving end in Guangdong to VSC?
LCC
等一下，我找一下。Wait for a moment. I will turn to that slide.
Excuse me, sir.
So,
你说吧。
do you mean are we going to use all the we are going to use VSC technology in Guangdong area in the future?
Yes.
Yes. If the DC system is located in Guangdong in the multi-field area, we will recommend it using VSC technology because the AC system is already no longer strong enough to help the 8 LCC HVDC to install. If we put, okay, can you see my slides?
No.
Okay, I will show it again.
Share your slide.
Can you see my slides now?
Yes.
If another HVDC is put in this area, we will recommend using VSC HVDC. But in the future, more HVDC system is located in other areas. For example, here, the HVDC is not put here. There are not so many LCC HVDC put here. We can use more LCC here. We are avoiding using LCC here.
Okay. Understood. Another question is how big is the difference in costs between LCC and VSC technologies?
Okay, the VSC HVDC has been developed very fast in the last 10 years. In Luxi back-to-back VSC HVDC, the VSC is almost 2 times the price of LCC, 2 times in 2016, and in Wuzhongde project, the VSC is about 40 to 50% more expensive than LCC.
Okay, thank you.
Question? Shall we take a break if you don't have any question?
Okay, let's have a break.
Okay. Let's come back at 4 o'clock, okay? See ya. Thank you, Dr. Zhou.
Oh.
See you.
See you, thank you.
See you.
Well, let's get started. It's 44. Do we get started right now? Hello, ladies and gentlemen. Okay, the second training courses will be taken by Dr. O. Let's get started. Dr. O, over to you.
Oh, come on. Okay, good afternoon, everyone. See you again. And I just, before my presentation, I just said that yesterday, PSCAD support have fit the problem of license. So you can apply the license again if you didn't have a license before. So you can, now the problem has fixed. So you can apply the license if you want. Okay. And then this is today for my presentation. The topic is power system simulation and testing technology. My presentation include 5 parts. The first is power system simulation technology and its application. The second is the real-time simulation and testing technology for HVDC system. The third is PSCAD, EMTD simulation technology for HVDC system. This is I have introduced yesterday, so I didn't introduce today. The other is the TS simulation technology for HVDC system, and there is conclusion. There is a real-time simulation. First, we will go to power system simulation technology overview, and then it's real-time simulation, and then it's power system PSCAD simulation, and then it's TS simulation technology. Three kind of simulation tool. So first, we will go to power system simulation technology and its application, the first part. So we first go to overview. What is the power system simulation? This is the definition of power system simulation. Perhaps everyone know well. I just show you here. Power system simulation is establishment of models based on the original power system and use the model for calculation and testing or study the work behavior of and character of power system within specific time. So this is power system simulation. And what kind of simulation tool in our power system? We think that the simulation tool can classify 3 kind of tool simulation. First is EMT simulation. EMT simulation is electrical magnetic transfer simulation. This is EMT simulation. Another is TS simulation. TS is electrical mechanical trans simulation. This is EMT simulation and TS simulation. And also another have a EMT and TS hybrid simulation. So this is three type of simulation. For EMT simulation, we can clarify as lead time and no lead time. EMT simulation for lead time is like RTDS. RTDS is lead time digital simulator. Simulator is RTDS, and also I have RTLab. For no lead time simulation, like PSCAD. Yesterday I have introduced PSCAD, EMTDC is a no lead time simulation, and also EMTP like this. For TS simulation, we have some lead time too, and also most of TS simulation is no lead time. Like DSP is a software development by VSC. We will introduce next training call. We will introduce the DSP as software, and also BPA software for also very popular, and also popular TS simulation tool is PSSE. This TS simulation. Sometimes we use the EMT and TS hybrid simulations. For this EMT and hybrid simulation, like also have lead time and no lead time. For lead time, we have a SMART. SMART is a super mix and lead time simulator developed by CSG, also by ourselves. This is a SMART simulation tool. And also no lead time EMT and TS hybrid. Also DSP, and also have a EMT and TS hybrid simulation. He can do this. Also NetMark can do this. No lead time EMT and TS hybrid simulation. So this is simulation tool for power system. And just now I have introduced the EMT simulation and TS simulation. These two kind of simulation is have many different big difference. What kind of difference we can see? For EMT simulation, the frequency length is for frequencies is he include harmonic. But for TS simulation, harmonic is not include, not care about the harmonic. Only the foundation the waves, only the 6 Hz or 50 Hz, only the foundation. For EMT simulation, he will care about the harmonic. For EMT simulation, he use phase A, phase B, and phase C to the power system. But for TS simulation, so no phase A, no phase A, B, no phase A, B, C. It's positive, negative, and yellow seconds. He use positive, negative, and second. He use his not each phase. He use positive, negative, and yellow. This is for phase. For simulation speed, for EMT simulation, it's very complicated. So the simulation speed is slowed. For TS simulation, we can, because he's only care about not care about the harmonica, so it's simulation is very fast. For the simulation square, the EMT simulation can only do a very do a small power system simulation. For TS simulation, you can simulation a very large power system. For simulation stamp, for EMT simulation, the simulation stamp is normally is seconds, microsecond. For TS simulation, it's milliseconds, the timestamp normally. Typical program for EMP simulation, just now I have said it's EMTP or PSCAD, this is no lead time, or RTDS, is a lead time EMT simulation. For TS simulations like DSP, BPA, and PSSE, also PSASP, like these two. This is EMT and TS simulation. And also for lead time and no lead time simulation, it also have many different. For the lead time simulation, the simulation speed is the same with the actual power system. That's to say, the speed of actual power system is what? Then the lead time simulation is what? So the simulation speed is the same with the actual power system. For no lead time simulation, the normally is smaller than the simulation is normally is slower than the actual power system. And for the simulation square, lead time simulation, because he should be lead time, so he can only simulation a very small power system. For the no lead time, we can simulation a large power system. The main difference of the lead time and no lead time simulation is for lead time simulation, he can be able to connect with the actual control and protection cubicle. So for lead time simulation, he can connect with a really physical control and protection cubicle. For no lead time simulation, he cannot able to connect with the actual control and protection cubicle. This is the main difference between the lead time and no lead time simulation. Also, qualification of lead time, we have a physical simulation of lead time, digital simulation, or hybrid simulation. This is physical and digital hybrid simulation for lead time simulation. So this is an overview of a power system simulation. And then another, I will introduce the development and application of power system simulation in CSG. How CSG's development and application the power system simulation technology and tools. To introduce this, first I will repeat the overview of power system of CSG, because the simulation is for power system operation and testing. So we and also my colleagues have introduced the CSG before. I will first also repeat a little bit. In China, we have two power grid component in China. The first is the state grid component of China. This is SG. It has the biggest, very big the power system. For CSG, this is China South Power Grid. Only the 5 provinces, for 5 provinces. Other is state grid, CSG, SSG. We are CSG. SSG is bigger. So CSG is it's from 2002. It's standard. And then this is the CSG information, and also have introduced before. And then what kind of simulation CSG use, because the character of CSG is very, very complicated. The first is CSG is AC and DC interconnector network. You can see we can many kind of DC HVDC transfer from east to from west to east, and also AC system and also can operate in parallel and dense, and also the distant and large capacity transformer. So because the communication the character of CSG is very complicated. So we have a challenge of simulation the AC and DC power system and testing in CSG. We have many challenges. The first challenge is large capacity power electrical equipment lies. So for simulation of this power electrical equipment like HVDC and STATCOM, because it's very complicated of HVDC and STATCOM, so we need to need many useful simulation tool to simulate it. This equipment, this is equipment need. And also for the AC and DC operation in parallel, we want to simulate the AC and DC interaction of AC and DC power system. This for system lead. So we should simulation it more in detail. And also many HVDC is in feed in Guangdong area. So we have HVDC much in feed. So this is also another challenge. Another challenge is specific operation model of HVDC, because in Yunnan area the HVDC both operation in island model. And also the Yunnan and Guangdong and the main CSG power system, he is connected by HVDC by VSC HVDC. So this is another challenge. And also for this several years, the development of an application of a new energy also development very fast. So we also have need to many kind of simulation tools to simulation the new energy device and their impact on the power grid. So it is also is equipment and system lead. So we have many challenges to simulation the CSG. So we want to develop the simulation tool to study CSG. This have a picture so how the CSG development simulation tool. The simulation tool development is according to the power system development, because with the development of power system, the simulation tool is also need to development. You can see that before the 2000 years, for CSG, it's normal, it's AC system, no HVDC, only AC system. So we only use PPA. The TS simulation tool is okay. It's okay. But after 2000 years, we have LCC HVDC. So we have input EMTDC or PSCAD, EMTP or PSCAD to study the power system, because we have LCC HVDC in our power system. And also we have import have by the RTDS, the real-time digital simulator to study the HVDC, LCC HVDC, about in 2004, because they have a LCC HVDC have put into operation. And in about 2010, we have STATCOM. We have STATCOM operation, STATCOM, and also have a VSC HVDC. So we have developed smart, and also have by RTLab to study the power system, because the power system is bigger and bigger, and also it's a more complicated. So also for 2015, we have developed DSP software by ourselves. So, and also for these several years, the new energies like wind power and also solar power like this have developed very fast in CSG. So we also have a new simulation platform. It's developing. We have now is developing some new simulation tools to study the power system. So for CSG, with the power system development, we also have developed many kind of power system simulation tool to study the power system. The first is and the second, the other is the general introduce of RTDS, real-time simulator. The other is real-time simulator. For real-time simulator, we have most is use RTDS or RTLab in CSG. In the session 2 review below, we will introduce the RTDS. For RTDS and RTLab, it's a lead time simulator. He is simulate with RTDS and RTLab. We also from Canada. Is useful to study HVDC and also power system study. This use RTDS and RTLab. RTLab is normally used in VSC. Another is the EMT simulation or live PSCAD, and this no lead time EMT simulation, live PSCAD and EMTP. Yesterday I have introduced this in detail. So this today I will didn't introduce, and also I will introduce the TS simulation. This is live DSP and PPA. For DSP, we will introduce next time. So in here today I will just introduce the TS simulation of HVDC model. TS model. This is below. Okay, so first I will introduce the lead time simulation and testing technology for HVDC system. So it's lead time. First, I will introduce the development of lead time simulation and testing technology in CSG. I will first generally introduce. What will we will introduce next? Well, we have three kind of introduce. First is for lead time simulation tool. Include RTDS for EMT simulation, lead time simulation, or smart for EMT and TS hybrid simulation. Also APGA For MMC simulation, this is a simulation tool for lead time simulation. 3 kind of simulation tool I will introduce. And also another is I will introduce a simulation model. Many kind of model, lead time simulation model, like the multi-in-feed system RTDS model, and also smart simulation model, also LCC RTDS model, also small timestamp RTDS model, small timestamp. And after they have a tool and model, we will introduce the simulation lead time simulation tool, simulation platform of lead time simulation, like LCC RTDS simulation and testing platform, VSC, this is safety and stability control RTDS simulation and testing platform, and also VSC RTDS and testing platform, and also STATCOM platform, and also a physical, digital, hybrid, microgrid simulation and testing platform, and also we introduce the dispatcher and operator training platform. So this is the general introduction of the introduction today. First, I will introduce the simulation tool for development of real-time simulation and testing technology in CSG simulation tool. First tool is RTDS simulator for EMT simulation. So we have a RTDS simulation laboratory in CSG. The laboratory is a CSG key laboratory for power system simulation. Was put into operation in 2004. Originally, it's for HVDC simulation and technology. But now we have many large kind of RTDS. Now have up to more than 60 rack. They're also updating and enlarging 60 rack of RTDS. The scale of its parents ability rating top in the world, so it's very famous in the world. We have a novel code, RTDS novel code, novel code card, PP5 card, and RS switch, like the GTNet, like this, or the GTA bit, PJ and GTIO, like this. Now it's very useful for the AC and DC power system simulation, testing, and analysis. I just now have said we have the past RTDS is from the first 4 leg is buy from put into operation in 2004. It's in Kent Road in Guangzhou. Only 150 square meter, and also another, and from the RTDS we have enlarged many times. In 2006 we also have buy 8 rack, and 2007 we have buy 12 rack, so totally 24, and also 2009 we also another two rack. So also it's 10 hollow. We have another location put in another location, and also now we have in Korean Road. It's the CSG. Now is the size of the lab. Our lab is more than 3,500 square meter now. Totally is more than 60 rack of RTDS. So it's the almost the biggest in the world. So this is our RTDS simulation system. So for this for RTDS simulation composed of now it's more than 60 racks. Besides RTDS, we also have many kind of control and protection system, like LCC HVDC control and protection system, cubicle of more than 10 HVDC project. And also we have some stability control and protection system of power grid. And also we have a new technology power system like STACOM, like this. So a new technology. Or we have a VSC HVDC control and protection system. All the control and protection cubicle is connect with closed loop connect with RTDS by the GT, by the IO card, IO input and output card. So we use RTDS to connect many kind of control and protection cubicle of the power system to connect together, to use this to study the power system of CSG. We can see use RTDS. We use RTDS to simulation the power system, and the control is by the physical control of power system. So we use RTDS to simulation the power system very useful. Useful for study the power system. So this is the framework of RTDS simulation power system in CSG. And then it's RTDS. Another is smart. This is smart simulator is for EMT and TS simulation, hybrid simulation for power system. What I will introduce smart here. This is smarter. This is to say we use RTDS to simulate the HVDC system. But for HVDC is in EMT simulation. But for AC system, we use TS simulation. That's to say we use TS simulation to simulate the AC system. Then we can simulate many large AC system. And then the RTDS and the AC system, we use the PC, parallel computer, so simulating the AC system. Then RTDS and the PC interface, have a simulation interface together, together. Then we can simulate the very large power system in real time. So this is the smart. This to say to VMT and TS hybrid simulation, real-time simulation of power system. We use the smart. We have a higher simulation precision than PPA, and also the simulation square of is larger than RTDS, and also we can study the power system more complicated, more flexible. So this is the smart. This is smart. We can see just now I have seen that we use the RTDS to smart to EMT simulation for EMT simulation, and also we connect to the TS simulation. For EMT simulation, the time stamp is 50 or to 100 microseconds. But for TS simulation, we use to 10 millisecond. these two kind of simulation tool, well, it's changed the data every timestamp. This say we use the EMT simulation to simulate the HVDC in RTDS, and we use PC to study to simulate the AC system in the PC, and then we can simulate a very large power system. We can see in the picture, the red one is the PMU curve of the really power system, and the smart simulation is the blue one, and the PPA is the green one. Green one is TS simulation. So we can see that the smart is simulation is better than PPA because we have care about the HVDC. The HVDC is used in EMT simulation, so it's more better. Simulation is more better. Another simulation tool is APJ. The APJ is for use to simulate the MMC simulation. Yes, VSC HVDC. So we use APJ to simulate the MMC simulation. MMC is a modular multi-leaf converter, such as STECOM and VSC. This one model or controlled. This is for MMC. Because MMC is switch very fast, so we use smaller timestamp to simulation the MMC. The simulation stamp is 2.5 microseconds. For LCC HVDC, we use 50 microseconds. For MMC, we use 2.5 microseconds in APJ. And also, we have many kind of MMC. First is V1, it's ML 605. But now it's used, version 2 is VC 707 FJ port to use. We can use CDS, we can use the RTDS, the MMC, we use the APJ, also connect to the RTDS. We can use RTDS simulation the AC system or LCC HVDC. We use MMC APJ to use APJ to simulation the MMC converter or controlled, and also we can connect with RTDS. So this is for MMC simulation, and this is the MMC valve model with actual controlled. We can see that this is we can see we use RTDS PP5 to connect to APJ, and then we use APJ to simulation the valve MMC valve model, and also use MMC to simulate the controlled of the MMC. He can connect together, and also he can connect with RTDS PP5 card. Then we can simulation with MMC valve with external controlled, external controlled. So we have a summit of the tool of simulation tool development. So just now I have introduced we can have three types of lead time simulation. First type is we use FPGA to study to simulation MMC. This is use small timestamp 2 to 3 microsecond in FPGA simulation. This we can simulate the MMC control and valve. And then we use RTDS to simulation the HVDC, LCC HVDC. His timestamp is 50 to 100 microsecond. The RTDS can also connect to the really physical control and protection cubicle. And then we use the PC parallel computer to simulate the AC system. This timestamp is TS simulation. His timestamp is normally 10 milliseconds. All the three kind of lead time simulation, he can connect together in the same simulation platform. He have an interface in each other, and the simulation data we can come from the EMS simulation, and also he can, after the simulation have finished, he can display in a large computer like this. So this is the sum of the lead time simulation tool developing in CSG. Okay, this is a table like this. So this is the table for the timestamp and time scale hybrid lead time simulation system for motor interior HVDC system is present, which is based on the FPGA plus RTDS plus PC. So we can see in the table, we use FPGA plus RTDS plus PC to simulation power system. The FPGA is to simulation the MMC device, such as TISCOM, STACOM, VSC HVDC. For RTDS, is used to study to simulation the HV system or AC system. For PC, it's used to simulate the AC system. And also for the simulation place, FPGA is very fast. EMT simulation. For RTDS, it's for EMT simulation. FPGA is more fast. RTDS is EMT simulation. For PC, it's TS simulation. And timestamp is like this. FPGA is 2 to 3. RTDS is 50 to 100 microsecond. PC is 10 milliseconds. So this is the simulation, the table. So this is table, the development of lead time simulation testing. And also another is the simulation model. Before I have introduced simulation tool, and then I will introduce the simulation model of lead time simulation. For lead time simulation, we can use RTDS model. How to set up the RTDS model? We have so the RTDS model process here. First, we need to dynamic equivalence of the power system, this first step, and then model and simulation, and then this model, check the model, verify the model. That's the three step. For the dynamic equivalence, also we have a three kind of dynamic equivalence, such as system equivalence for this serves purpose, and sometimes we use FDNE. FDNE is frequency dependent network equivalence. Two kind of dynamic equivalence. For modeling and simulation, we can data convert from PPA to RTDS, convert from PPA. PPA is the TS simulation program, convert to RTDS, and then we can check, and then the subsystem pattern of equivalent network, and then we can determination of the TT line between each subsystem, and then we can check the process source, and then we can do the check the simulation, set up the simulation model and simulation, and then after we set up the simulation model, we will check what is he have some problem about our simulation model. First is the power flow. Power flow is okay or not, and then is the state or dynamic character is okay or not. So we check the model is okay or not. So this is an RTDS model. We can show this is the matter in field system. RTDS model here is more than 36 rack, and all the 250 and 20 kV and above AC and DC power system of CC is included here. More than 10 HVDC is in here, and more than 1,000 node, more than 100 generator is included RTDS model. And also sometimes we use we just now have this, we said totally 36 rack is used in the RTDS model. We use 18 rack to study the DC HVDC power system, Another, we use the AC 18 rack to simulation the AC system. This is the RTDS, fully RTDS simulation, model. We have a AC system, also include the generator, also TC line, like this. And other is we have smart. This is every AC and DC, all the AC and DC is simulation in the RTDS. For smart, some is simulation in RTDS, some is simulation in PC. So for smart model, we will use the EMS simulator data. We will for the PPA data, API data. For PPI data, we can use PPA data for the AC system model, and also RTDS model is for the DC power system model. DC HVDC system model. And then the AC system model and DC power system model interface together, that will be the smart model. So with the smart, we use HVDC to simulate in RTDS, AC system simulation in DC is smart model. And this is the picture of how to set up the LCC HVDC RTDS model. We can see in the left side is the HVDC primary systems primary system. This is a configuration of the HVDC project, and then we will convert this project to the RTDS model. The right side is the RTDS model. The left side is the actual net of the HVDC project. We can see here. This is RTDS model. Our RTDS model, we can use the PSCAD, ASCAD. We had many kind of RTDS model. For the RTDS model, we use ASCAD and PSCAD is very similar. Yesterday, I have introduced the PSCAD. Today, for RTDS is ASCAD. They are very similar because they also developed by Manitoba Hydro, the same company. So for yesterday, I have introduced PSCAD. So I will introduce ASCAD in RTDS here. This is ASCAD for RTDS model. Perhaps this is not fleet. If you have RTDS, you have no ASCAD. We can note here RTDS ASCAD. You can see also many kind of simulation model here. For here, this is HVDC controller. This is for this one is HVDC RTDS control. This is for physical control because RTDS can connect to the physical control and protection system. So if I open this one, we can see here. This is RTDS ASCAD model. We can see ASCAD here. You can see this is the HVDC. Very simple HVDC. It's a monitor HVDC. You can see here. This AC system. It's a rectifier side. This inverter side. And also we can see here. This is some data of converter. This converter. Many kind of the parameter here like this. It's a very light PSCAD. You said that yesterday we have seen the PSCAD. You can see here it's a very it's ASCAD in RTDS. Also many Okay, continue. Okay, just now I have I have shown you the PSCAD model of HVDC. This is for this one. We see that the PSCAD model is a little like the PSCAD model. For this model, because RTDS, he can connect to physical HVDC control. So this model we can see he have no control, only have IO card. He connect, he will connect to the physical HV control. So his control, no control here in the model is no control because the HV control is use the physical HVDC control cubicle. So this model is a little simple. And another model we like here is this one is use RTDS model. Okay, here. Close it and open again. This one, for this one, as RTDS controlled. We can see here, this model is this AC system, and also this DC system. For the DC system here we can see the HVDC controlled. For here, we can see the HV control is here. Many kind of HV control, because in this model, we have no physical cubicle, no physical configure. So he used RTDS PSCAD software control. And right here is current and power system setting point control. And also here is rectified current control. Like this, many kind of control. So this model is use the RTDS software control, not physical control. So this is the RTDS. Another RTDS model you can hear AC system and also the controlled. This one. Another model is RTDS. You can see a bipole RTDS model. Another model. I will open this one. This one is a LCC HVDC bipole. Just now I show you it's monopole. This is bipole model here. We can see this is a bipole model. You can hear. Bipole. This is pole 1, pole 2. Pole 1, pole 2. Have 2 pole. 2 pole. It's more complicated. This one. You can see this model is more complicated. We also have many kind of control, like bipole control, also control sequence, also station 8, rectify, station 8, pole 1 control, station 2, pole 1 control, this station 1, pole 2 control, this station 2, pole 2 control. So you can see ultimately also the control is the software control of biport and biport. It's very complicated. So I just show you the ASCAD and PSCAD, the model. So you can see this is ASCAD model for RTDS. Yesterday have a PSCAD for MTDC. So I have shown you the two kind of model. This is for physical controlled. For controlled model, and also we have a software controlled, and also have a this is the software controlled, and also this have biport. I just have show you biport controlled. Now this is part PSCAD and ASCAD. And another simulation model is the small timestamp RTDS model. Just now I have seen the HVDC, low LCC HVDC, normally its timestamp is 50 microseconds. We call them as large timestamp simulation station. But for VSC HVDC or MMC converter, he used the small timestamp simulation. Is 2 to 3 microseconds for MMC simulation. The small timestamp and large timestamp have a interface here. So he can connect together. In the same model. So this is RTDS small timestamp model. And for the LCC RTDS, and then we continue the simulation platform. Just now I have introduced simulation tool, simulation model, and now is simulation platform. First platform is LCC HVDC RTD and testing platform. So I have tell you that we have RTDS is a real-time digital simulator, and RTDS he can connect with the physical HVDC controller, and also protection cubicle. We have in CSG, every HVDC have a physical control cubicle in our laboratory. The control and protection cubicle is closed, roof connect with RTDS connect together, so we can simulation the HVDC control and protection character very better. So this is a Gaozhou and Xin'an HVDC, and this is Tianguang HVDC. This is Yunguang UHVDC control cubicle here. And this is also an example. It's RTDS is connect with HVDC control cubicle. Control cubicle can include station control, port control, also protection system. He can connect with RTDS with IO card, IO's input and output card, and also have HMI. HMI is a human computer and human interface to operate the system. And also the RTDS and LCC HVDC platform, we also simulate the VBE, this wire-based electrode to connect inside. Only port one is use the VBE. There is to say, So V pole 1 DC measurement and P pole 1 P pole control is use the pole 1 VBE to simulation the VBE function here pole 1. For pole 2 is no VBE because we want to minimal the cubicle in a laboratory because the cubicle need much room for our laboratory. So this is VBE simulation, and also with the VBE simulation, and also this is HVDC measurement system simulation. We use RTDS simulation the HVDC primary system, and then we use the GTAO. This is the output signal output, like this current, this voltage, like this. He will transfer to the GTAO card, and then we also connect to the DC measurement system. And then after this measurement system, Optim DC measurement system, he will input to the HVDC control cubicle. This is so the DC measurement system also simulation in our laboratory. This is a picture of the HVDC RTDS simulation and test system. We have a RTDS here, RTDS simulator here. We have a HVDC control and protection system, like station control, hall control, protection system. All the cubicle here. It's no redundant because redundant need much room, many cubicle. So we no redundant control. And also the HMI is used to simulate the operation the HVDC and also have a LAN to connect all the system. Also, we have RTDS workstation to set up HVDC model like this and modify the model, also modify the parameter of control and protection system. This is the platform. And because the cubicle, you see, the control and protection cubicle need much room. Because he is very bigger, need much room. So we use developing the C++. That is to say, we use a very small computer to simulate the control and protection function of the control and protection cubicle of HVDC. We use a very simple PC to simulate it, and then connect to RTDS and HMI. This is C++. So C++ is why is used. This is used compact and modeling a DC and control and protection simulator. This is used. This is to reduce the room of the control and protection system. By use this one, and also we compile the C+ model and use and the physical control and protection. We have a compare together. So we can see that the red one is the C++, blue one is use the physical control and protection system. The red one is use a C++. It's the PC control and protection model. So we can see from this one, this picture, as it's very close, very almost the same with the physical control with C++ and physical control and protection system. So we have also development this C++ to simulation. And also this one and is RTDS to safety and stability control of CSG. Also, beside HVDC, we also have a safety and stability control of CSG. Connect with RTDS. Connect with RTDS. This SSC. SSC is safety and stability control. This is close in loop with RTDS. This is typical of SSC of CSG. Yunnan, Guizhou, Guangxi, Guangdong, SSC. Every province have a safety and stability control, and also is connect with RTDS. This is for with the SSC RTDS simulation and testing platform, we can use it to study the AC and DC power system character. Sometimes we can see that if the DC4 happen here, we can see we have some low setting station controlled. Also have generator chip controlled. We all have connect with RTDS. Then use this, we can study the behavior of SSC. That's safety and stability control. How is the behavior of the SSC when the fall happen in the AC and DC power system? So it's very useful. And also another platform is the VSC HVDC RTDS simulation and testing platform. This VSC HVDC. Just now I have said VSC HVDC. We use the GTFJ to simulation the MMC valve. So we use RTDS, GTFJ, and also we use RTDS PP5 to simulation the VSC HVDC control. It also have a physical control and protection device. And also we have the STACOM simulation and testing platform. Also simulation very similar to LCC HVDC, VSC HVDC, the STACOM. We also have a physical control and protection system of STACOM. Also connect together with RTDS by the IO card. And another is a physical digital hybrid microgrid simulation. Because now the renewable energy is developing very fast, and also microgrid, and also somewhere have some kind of microgrid. We also use RTDS to developing the microgrid simulation. We use the nice solar power device to connect with RTDS power system with IOCA or other. Also wind power like this. And also there's this display and operation training platform for the display center. We also use RTDS simulation the power system. We have a simulation input, and also the output. We use the we have a display of the simulation result, and then use to train for the display center. This engineer. This is a display and operation training. That is to say, the AC and DC power system EMS is power operation or power operations skills. We will input to the RTDS simulation system, and then we have a displayed platform. Display platform is just like the EMS picture. Then this picture here, you can see we can connect with RTDS. We have interface connected together, and then after the simulation, the result is input in the displayed platform, and the operator can do some control of the power system. He can do some control. After he control, the control also input in the RTDS, and RTDS operation will be changing. And then the operator can operation the power system in the simulation system. This is used to change the development display center. Another is an overview of application of the real-time simulation and testing technology. Just now I have introduced the technology of real-time simulation and how is the application. The application of power system simulation, we have several kinds. First is the test for the HVDC, technical support for the HVDC, whole life cycle. Another is AC and DC power system. Another is testing new knowledge of power system. Another is training like this. The first use of RTDS is the technical support of HVDC of whole life cycle. You see it. One HVDC project after his decide. After he decide, and then the cubicle of HVDC is manufactured, and then we use RTDS to do the APT and DPT of the physical HV control and protection system. So first, we use RTDS to do the APT, a functional performance test. This APT and DPT, dynamic performance test of HVDC when he is HVDC project. And after the HVDC project is put into operation, if some fault happen on site, we use RTDS to technical support for the HVDC on site. We can modify the HVDC software and check it's not improved or not. If we check that after our simulation, the HVDC have improved after it's modified, then we will give a report to the display center, and then the display center will modify the software of on site. So this is a technical support for the power HVDC operation. So this is the use of RTDS to tech HVDC project and technical support. Also planning. Sometimes when we do the planning of HVDC, we also use RTDS study what kind of planning is okay. It's better. So it use RTDS. And also we do now we can see the APT and DPT in CSC of HVDC. We can see use RTDS to connect with the physical control and protection system of HVDC cubicle, and then use this to test the function of and dynamic of the HVDC control protection. When if he some have problem, we can find problem after during the APD and DPT, and then to improve the software of the control and protection system. So it's very useful for the HVDC project. And after it also just now, when the HVDC4 happened on site, we use RTDS to simulation the fault in the laboratory, and then we found the problem. What is the kind of problem? And then we will present a report to the dispatch center, and then we will modify and the software, and they will improve. We can see that this is some case before we have it's not good. After our modify, it's more better. So this is our simulation technical support. Another is technical support for the HVDC isolating model technical support, because some HVDC in CSG we need to isolate model operation. This is some problem. Normally, is the governor is tenant of generator have some impact on the HV operation. So we use it to use RTDS to study the problem and fix the problem. And also technical support for the AC and DC power system operation, not only HVDC, also AC and DC power system. For some case, it's only use PPA. He cannot simulation the power system very well. So we use RTDS to check the really function or character of AC and DC power system when in some series case. So because RTDS is much simulation is much better than the PPA, because you have many HVDC in CSG. So the character of AC and DC power system is very complicated. So we use RTDS to study and the problem. And also we can see why we use RTDS to study the AC and DC power system. We can see the black one is PPA simulation. The blue one is smart. The red one is RTDS. We can see that the PPA simulation is the RTDS simulation is much better than the PPA, because RTDS can simulation the AC and DC power system very well, and also the RTDS simulation is much better. It is almost the same with the actual record of the power system. So it's use RTDS to the post-fault simulation and analysis for the power system. This is the RTDS simulation with the really on-site record. We can see the RTDS is almost the same with the on-site record. And also another tested use is is a new technology, testing and analysis, like master HVDC coordinating controlled, SVC controlled, TCSC, storing energies, wind power, solar power, DC DIs, like this. It's many kind of new technology. It's use RTDS to study and testing. And also for technical training for the AC and DC operator and dispatcher, because use this to study the to training the operator and dispatcher, and also technical training for AC dispatcher, HVD operator or dispatcher center. We have every year we will use RTDS to train the dispatcher center engineer every year. Another is PSCAD simulation and technology. This is I have introduced yesterday, so I didn't introduce today. So I just next one. Another is the TS simulation technology for HVDC system. Just now I have introduced the lead time simulation and testing technology. And yesterday PSCAD EMT, no lead time simulation technology. Now is we introduce the TS simulation technology for HVDC. For the TS simulation of HVDC, we will have some a simple thing. The first is the communication bus. Voltage is a science where it's a very good, and the frequency is constant, and the three-phase balance of converter, three-phase balance of converter, and also the impedance of the smooth reactance is very great. There's no leak of the DC current. Another is the character of the valve is very ideal, very good. The valve is very good, and also each valve is chipped in turn if the same time. So this is the equivalent of HVDC system. This is UAC. This picture you can also everyone know this. This DC voltage is calculated by this one. So the TS program is use this to calculate to in his software, and then it's this current is calculate like this, IDC like this, also the register is like this. So you can see it's very simple in the TS software. TS software for HVDC model is a little simple. And then the program for TS simulation program is like BPA. BPA is by EPI of China. Development by China, EPI. But this is BPA is originally is developed by American and development by China, EPI. Also have we have developed many years in China, PPA software. So it's very useful, very popular in China. For some of you, we can know that we use PSSE, but in China, most is used PPA. But now in CSG, we have a few developing a new TS program in its DSP. This will introduce